We're going to be testing the significance of the correlation coefficient, and we're going to kind of launch right into it. We've done lots of hypothesis testing throughout this course. Um, you're going to have the same setup here. We're going to have to figure out what our hypotheses are. We have some assumptions to check. We got to figure out what a test statistic is, what distribution it follows, and then we follow up just like we always did. The reason this is important is because we had talked in a previous video about how we needed to make sure that there was some linear correlation present in order to make a prediction using the regression equation. And again, make sure we understand that's the key point of this whole chapter. While we're doing everything we do in this chapter is to make predictions. And so we had those three criteria we had to check in order to see could we make a prediction. One of those was we needed to see if there was any linear correlation present. And that's what this section is going to attempt to answer for us. Before we get to the section, we could have just said use our rules of thumb and say any correlation value that's less than 0.25, we would call that no linear correlation. And so we would say we should not be using that for prediction. Any time that R exceeds 0.5, we would say that's at least moderate linear correlation. So we could use it. And then in between 0.25 and 0.5 is kind of a gray area where it's maybe look at the other two criteria. Well, now we can be a little more precise with that rather than just using rules of thumbs. We can actually do a statistical test to see if rho is equal to 0. Notice in this case, all three of our possible hypotheses, the null hypothesis is rho equals 0. We don't really worry about making sure that we have greater than or equal to or less than or equal to in the null hypothesis. Why is that? Because rho, being the population linear correlation coefficient, goes from -1 to 1 just like R does. One's just the point estimate for the other. In that middle one, right? That middle hypothesis there, the alternative is that rho is less than 0. So the opposite of that isn't necessarily that rho is greater than or equal to 0, because then there still is correlation. It's just the other direction. So we're actually interested, there's kind of two opposites, right? There's opposite in the terms of the direction, but there's opposite in the terms of is there any correlation present? And the latter is what we're actually interested in. So in this case, it would actually be inappropriate to use greater than or equal to or less than or equal to in your null hypothesis. The null is always equal to 0, because what we're saying there, if we've done a lot of hypothesis tests with just words. If we wanted to just put words for a hypothesis, for the null hypothesis, we would just say there is no linear correlation in the population. Notice it's rho, not R. R comes from the sample, rho comes from the population, but they measure the same thing. So the null is that there is no linear correlation in the population. And then the alternative in words would be, the first one would be, if there is some linear correlation in the population, I just don't know what direction. The second one would be, there is some linear correlation and it's specifically a negative one. And the third one is there is some specific linear correlation and it's a positive one, again, in the population. Okay, so this section we're just going to work through. Can we conclude, because again, remember the alternative is what we conclude at the end. And so we're either going to say we can conclude that there is a linear correlation in the population, or we cannot conclude that there is a linear correlation in the population. And again, two of those three options specifically, we could or could not conclude that that correlation is positive or negative. We have a lot of assumptions on this one. It gets a little bit out of hand. We're just going to run through them. The first one, as always, sampling methodology. Again, the same thing happens here as with everything else. We are taking a sample and using that to make an inference on the population. So we have to say, is the sample looking enough like the population in order to justify making that leap from a small amount of data to making that inference on the larger amount of data from the population? So same thing you've always heard, always looking at, always checking our biases, making sure that we have a representative sample. Number two, there's a linear pattern to the data. Why is this important? We want to look at the scatter plot and say to ourselves, if there's a linear correlation present visually, then we can go ahead and test statistically, do we have that? The idea here, maybe you want to make a note about this, it's specifically if I see a pattern that is not linear, this is not appropriate. If I see a quadratic pattern, a cubic pattern, a sinusoidal pattern, any other pattern that you could say, that's maybe you can even name it, just say there's a pattern to this and it isn't a straight line, then you would say there might be some correlation, but it's not linear. Or you might be able to determine there is a quote unquote linear correlation, but there's a better correlation out there. And so you say, well, what would you do? Well, we're not going to cover how to do it, but what would you do is there are ways to transform the data and do different things. We would go down that rabbit hole to say there's better methodologies that fit the type of pattern that that data shows us. Okay, so we always want to look at the scatter plot and say, if there's a linear pattern or there's at least not some other pattern that I can see, that's what I'm looking for to give kind of clearance. You may not see a scatter plot. If you do not see a scatter plot on this one, you're just going to kind of move forward and say, hey, we're going to assume that this is an appropriate test. Okay. Second one, the standard deviation of the y's are equal for all possible values of x's. This is called homoscedasticity. It's a fun word there. What this means, maybe you want to make a note about this specifically. You do not see in the scatter plot a fanning pattern like starting off where all the points, if I'm looking left to right, reading it like a sentence, all the points are really close to each other and then fan out further away from each other, making like a megaphone. Or vice versa, that again, reading it left to right, that all the points are really far apart from each other, but then they get gradually closer and closer together. Again, like a megaphone not going the other direction. We don't want to see a megaphone. Okay, we need to make sure that if I take a freeze frame of every x, so make a vertical line with your hand over the plot and say, for that x, look at all my points. Is the, because standard deviation spread, right? Are the points, are the y's spread out the same there as now move that vertical line further to the right? Are the y points spread out the same there? We want to make sure that as we scan this thing left to right, that the spread of the y's is about the same throughout the entire plot. And again, that's going to require a scatter plot. If you don't see a scatter plot, what you're looking to do is I want you to write down the assumption, know the assumption, and kind of say this is something we need to check, and we don't have a picture for it. We need, make a note to self. We need to look at the scatter plot for this. If one's not provided, that's an important step. Now we've got two assumptions that are going to require us to have a scatter plot. Next one is there are no outliers. Again, now we need a scatter plot for the outliers. Okay, now we haven't discussed a formal definition of an outlier. There are many different ways we can look at this. We can look at an outlier based on the x-axis. We can look at an outlier based on the y-axis. We can look at an outlier based on the trend. So this is a very broad one. And again, we need a scatter plot. So this is 3 in a row now that we need a scatter plot to look at to say, are there any outliers? This one, for our purposes, we're just going to use the I-test. In a more advanced course, if we had an upper level regression course that you were taking, we would spend a week or two on just this one bullet, how to assess outliers. It's very complicated. There's a lot of different ways to do it. And so we're not going to stress about that. We're just going to say, look at the scatter plot and just kind of eyeball it and say, do you see one point that looks really weird? Whether that's really weird because it's super far away from all the other x's, really weird because it's super far away from all the other y's, or really weird because it's just super far. Maybe the x value, maybe it's not a weird x value in and of itself, and maybe it's not a weird y value in and of itself, but the point itself just is really far away from the rest of the trend. Okay, we want no outliers. Again, if you don't have a scatter plot, you're going to need to make sure that you note, this is what I'm looking for, and I need to check the scatter plot in order to be completely sure that my results hold. Next one, the residuals are independent. And so now, remember we talked about residuals previously. That is the difference between the actual values and the predicted values. And we need to make sure that if we look at a residual plot, that there is no pattern to it. What it basically means is I don't want to be, here's what we're talking about. And this one links back to that first scatter plot check for is there a linear pattern. If I'm constantly I don't want to constantly overshoot early on and then constantly undershoot later. Or I don't want to overshoot and then undershoot and then overshoot. It's one of those things where if you just look at you can look at what's called a residual plot, which is a separate plot of the residuals. If you had think about how in a previous chapter, or excuse me, previous section, we would take data from MyOpenMath, plug it into Excel, and we could find the regression equation. So you had a list of x's and a list of y's. And that next column, you could make a column of y hats of all the predicted values. You have a regression equation, type it in. Type it in right there. The regression equation is 4.3 plus 1.2x, whatever. Type in equals 4.3 plus 1.2, multiply that by whatever that x is, and then do that for all the values. Now you've got a list of all the y's and a list of all the y hats. Make another column and do the one column minus the other column. That's the residuals, y minus y hat. Then you can plot those. Okay, you plot them specifically against the x's. So now you would do like a new scatter plot, but the x's would still stay on the x-axis, but instead of the y's on the y-axis, you'd put the residuals. So we can look at a residual plot and see, is there a pattern to it? Or, kind of as I was mentioning, if you just look at the scatter plot and you have the line that goes through it, just kind of see where you're missing. Because again, the points are not going to be in line. That's fine. We know we're going to have errors. That's not the problem. But we want the errors to just be randomly up and down, above and below that line. We don't want all the points to be missing above the line for a little bit and then kind of most of them below the line and then most of them back above the line. If we see some weird pattern like that, what it's telling us is, going back to that second bullet, that we don't have a linear pattern and we shouldn't have done this in the first place. And the last one is the y values are normally distributed for all possible values of x. This is one that we just kind of have to make this as an assumption and just kind of say we hope it works. We are not going to discuss how to check that, and oftentimes it's hard to check that. What this means is that there's not a clustering of y values that are skewed high or low for certain x's. It's something that we're just going to have to kind of say, look, we need normality in our y's. Make sure we understand this. So we don't need normality in our x's, and we don't need normality in our y's as a group. We need normality in our y's for each x. And this is where this section gets a little bit galaxy brained. We have to think about the fact that you may only have 5 points of data, 10 points of data, 15 points of data. So this is why we said all possible. Don't think about the fact that your data set is 10 observations. Think about your x's versus your y's. Let's say your x's are age and your y is height. And we're talking about kids, so we know we'd have a reasonably linear pattern. For all x's means when you have kids who are age 6, would the y values of height be normally distributed for all 6-year-olds? I would say, yeah, probably so. Like most kids are about the same height, and you have some tall kids and some short kids. Okay, what about for age 7? Are the y values normally distributed for all the kids who are 7 years old? And I'd say, yeah, sure, same thing. Most of the kids are about the same height. Some kids are tall, some kids are short. What about for age 8? What about for age 9? What about for age 10? Okay, and that's this idea that we just need to make sure that if I condition on only having x's of one number, are the y's normally distributed? The y's overall maybe wouldn't be normally distributed, because that would say that the height of all kids is normally distributed, but that might not be accurate, because if you have kids that are really young and older, that might not be a normal distribution. That might be more of a flat distribution, right? You have a lot of people who are 2 foot tall, a lot of people 3 foot tall, a lot of people 4 foot tall, a lot of people 5 foot tall, right? Wouldn't really be a bell shape. It's that we have the bell shaped distribution for all the 6-year-olds, for all the 7-year-olds, for all the 8-year-olds, etc. Okay, and that's going to be harder to check. It's going to be something more so that we need to have a little bit of an expert knowledge in the field in, and or we're just going to say this is an assumption we're making. We're branching into, as we wrap up this course, we're branching into an area of statistics where we might need a little bit more expert opinions to satisfy some of these assumptions. So from our job analyzing the data, it's simply to say, these are things that someone needs to come back and tell me if that's reasonable, because data-wise, it's harder for me to figure it out. And maybe one day you'll be on the other end of that spectrum, and you will be the expert in that field. And they'll ask you that. They'll say, hey, does it make sense that the height of all 6-year-olds is kind of a bell shape? And you'll say, sure. What about ages or heights for all 7-year-olds? And that's something we all kind of can get a handle on. But when we talk about different types of data, there'll be things that you and I might say, I don't really know the answer to that. We need to talk to someone else and see, does that seem like a reasonable assumption? So your job with that condition is just to say, this is an assumption that we need to make sure is met. And if it's met, then our assumptions are good. And if it's not, it might cause a little bit of error in our results. Our test statistic, we are back to a t-test statistic, but our degrees of freedom are n-2. Without diving too deep into that rabbit hole, if you think about it, we had a one sample t-test And our degrees of freedom were n minus 1. When we did standard deviation, right, we had to divide by n minus 1. There was one variable. Now we have two variables. So now our degrees of freedom are n minus 2 because there's two variables. There's an x and a y. There's not just one variable. We're going to take the value of r multiplied by square root of n minus 2 divided by square root 1 minus r squared to get our test statistic. Again, that follows a t-distribution with n minus 2 degrees of freedom. Now we're back to the world where you might have left tail test, right tail test, and two tail test. Check your alternative to answer that question. Take note, if you do some Googling, if you look at a textbook, there are other formulas for this. They should be the same though. It's just derivations where it's written a little bit differently. I showed you one of these in a previous chapter, I believe it was chapter 4. I gave you the formula for the population standard deviation of a discrete random variable, and then we rewrote it a little bit differently. Same thing here. I'm not giving you both formulas because I think the other one is a little bit more confusing. But if you see something that looks slightly different, they're just deriving it and making it look a little bit different, but it's going to give you the same answer. Okay. And the last piece is, again, the same two things that you've written probably a dozen times in this context by now, and then many, many more with regards to working the actual problems.